Good afternoon and welcome to this week's edition of the CERIAS Security Seminar for Purdue University. Our speaker today is Dr. John Feddema. He's a manager of Data Analysis and Exploitation Department at Sandia National Laboratories, and he supervises a department specializing in signal and image processing. Also proud to say that John got his PhD in electrical engineering here at Purdue University. Welcome, John.
Thank you. So I'm going to talk about evaluation of urban vehicle tracking algorithms. This may not be exactly tied to cybersecurity like you're thinking, but I think that there is some parallels that I'd like you to think about. Whereas we're looking at and interested in trying to find multiple vehicles over, as shown in the left, there's a road map, and this happens to be Socorro, New Mexico. On the right is an image taken from the Sandia Peak looking down at Albuquerque, and hundreds of cars that are moving at night and trying to detect and track those cars at a resolution where you don't have what usually is called enough pixels on target to distinguish the cars, but you get glimpses of the cars. You get maybe a car shows up in a pixel or two, because we've got probably 1 to 2 meter resolution in this particular image. And so the difficulty gets to be, you get instances of somebody moving in this environment, you get observations, and you've got to go and predict what they're doing. Now, I guess the cybersecurity parallel would be you're looking at a network intrusion sort of application, and how would you apply some machine learning algorithms or signal image processing algorithms to determine where that intruder is moving through your network. So kind of think of this as in that parallel sense to try to visualize how maybe some of the same sort of ideas or algorithms could be applied to a security network application. Okay, so in general, Sandia does do work in the area of nuclear non-proliferation. And we do have satellite systems that we work on, and in general, my department does detection, tracking, classification. So a lot of this work is related to this idea of how do you scale up detection when you've got a large number of detections and tracking objects that you've got to look at. Okay, so I'm going to switch before, let's go to the next slide. So the difficult part with this tracking application is really there's on two extremes. On one extreme, you've got where we do just blob detection. You look at just a blob and how it's moving. And if it's a single pixel, it's usually easy, like a Pac-Man sort of thing, to follow a single pixel moving in an environment. The difficulty gets to be when you get noise and you're looking at objects that are very low signal to noise ratio, meaning they're just barely above the noise, the dark current noise in the sensors and things like that. On the other extreme, you've got physical security applications where you may have, I may have cameras here looking at all of you, and I may be able to track every one of you moving around in this environment. And one of the reasons I'm able to do that is because I get many pixels on target. I can distinguish. You're not just a blob to me. I can see the whole shape. I can do the association from one blink of an eye to the next blink of an eye, and I can see not only where you were in the previous frame, I can see you in the next frame, and I can distinguish. I'm at the same time doing the facial recognition that says where you are. So you have the two extremes. One is I've got lots of pixels on target. One, I've got only 1 pixel on target. And what we're interested here in this urban tracking is somewhere in between. You might get a few more pixels on target, but we still don't have enough to have lots of pixels on target where you can do discrimination easily. And then you've got the other problem of occlusions and overlaps and vehicles that come in and out of focus because, again, they're low signal to noise. If we're looking up on top of Sandia Peak over 3 miles looking down at a bunch of cars and the cars move and turn, you sometimes get a glimpse of their headlights, you sometimes don't get a glimpse of their headlights. And so you've got to take into account the fact that you might see it one instant and then you get several frames where you don't see it and then you've got to see it the next instance. And when you've got 2 cars that are crossing, how do you deal with that? Or multiple cars going in parallel, or maybe one going past the other. How do you associate when that one car passed the other? How do you associate? And then the other problem is we typically, when we're tracking objects, we use some sort of model or dynamics of the object. Usually a Kalman filter is the approach most people take. Kalman filters are great if you got a nice continuous motion. If I'm looking at a missile trajectory, a nice continuous motion is, Kalman filters are perfect for that. Cars, though, traffic starts and stops. And so that's a very difficult problem. So how do you deal with the fact that not everything moves at a constant velocity? There's acceleration starts and stops. There's right-hand turns. How do you deal with all of that? I'm going to switch to, I wanted to show you one other slide here. That I had up just a minute ago. So this diagram here shows the typical sort of detection and tracking diagram of how typically this is done. So you can see that block that says raw sensor data. That is the raw sensor data of, say, some CCD-like camera looking down at, say, Albuquerque. And what we typically do is we take the current frame and we subtract off a background estimate of what's behind or what's the normal scene. So think of if I had a bicycle going through an environment, and I might first take a picture of the scene before the bicycle moves through the environment, and then I take a picture as the bicycle moves through, and I take the current frame minus that previous frame. Then I'd get just the bicycle, hopefully, and not the rest of that environment. It'd be subtracted off. That background estimate, though, there's a lot of different techniques for doing that. We're not really going to discuss that here. There's all sorts of, like an infinite impulse response filter, or some what's called a fast approximate power iteration algorithm, where you're doing singular value decomposition on the image. But the fact is, we get a change where these first two blocks between the raw sensor data and the background estimation are doing a background change detection process. That then you're going to go to this next box that's going to do a thresholding. And so you get these detections out that are above a certain threshold. They could be the actual object you're tracking, or they could be noise. They could be things like, because the camera is sitting on top of this peaks a mile up, and there might be wind and breeze moving it around, you might get a little jitter in your camera motion. You might get noise associated with just blinking of the city lights. And you got to take into account all of that. The main part I'm going to talk about in this presentation is the lower right, which is how do you do the observation, observation to track association. How do you do the gating? Gating is if I've seen it in one frame and I move to the next frame, I expect it to move a little bit but be approximately here. And I put a gate or a circle around it, and I say, well, if anything that observes in the next circle, then I think that that's the same object that I saw in the previous frame. So that's a gate. Then I do a prediction and filtering. That's usually a Kalman filter that says where it's moving next. And then I do track maintenance, which does either a whole new object or a car moved into the scene, or that car just turned off its lights and now it's no longer in the scene. So you got this initiation, confirmation that it's still there, or deletion. So I'm going to be talking mainly about that lower right set of boxes. Now going back to this presentation. So what I'm going to talk about is a couple of things. I'm first going to talk about the 3 data sets that we collected data from, and then I'm going to spend most of my time on these 4 tracking algorithms that we evaluated, talk a little bit about the evaluation metrics and the results. And again, I think if you look at these algorithms, they could be used for network security. So this RANSAC algorithm is a very popular algorithm, goes back to the 80s, and it's a way of removing statistical outliers. And then using a least squares fit of those things that are outside of the statistical outliers to say, that's the model that you're tracking. The proximity tracking algorithm is our own homebrew algorithm. Monte Carlo, or Markov chain Monte Carlo data association. Markov chain Monte Carlo techniques are used throughout computer science, so you could definitely use this technique for a network sort of application. Tracklet inference, factor graphs are a Bayesian graph approach. Bayesian network approach. And so, again, this probably could be applied to a cybersecurity problem. So the data sets that we had, the one in the lower left is, again, these city lights looking at Albuquerque from up at the Sandia peak. The one in the middle is we used a Sumo simulation simulator that's freeware out on the net, and we simulated 780 vehicles moving around. The video of the Albuquerque, we only by hand picked out 11 vehicles that we truthed. There were hundreds of other vehicles that were in that scene, but only 11 that we truthed. We used the simulator to, it's always hard to get ground truth on what is really moving through the scene, so the simulator was a way of testing the tracking algorithms without getting it mixed up with all sorts of other noise. Another data set that we looked on the far right is Air Force Research Labs out at Wright-Patterson had a UAV flying over 3 different areas of interest, or regions of interest as shown over here, and they had ground truth data on 60 to 100 cars, and so we used that data as well to try to ground truth these 4 different algorithms. So I'm going to start off by talking about the RANSAC technique. So all of these techniques require some sort of motion model. So this is the dynamics of the system, and the easiest thing to do is assume a linear dynamic system. So you got, looking in an XY plane, you've got of a constant velocity model that says, how does this move at x1 is your initial point, times the velocity times the change in time, how far has it moved, okay? So we just got this constant velocity model. And if you're familiar with common filters, you use that, plus you add some sort of white Gaussian noise to it, and then you use the common filter to weigh your observations based on how good you think the observations are versus how good you think this model is. And so you're optimally weighing the observations versus how fast the model is moving. The RANSAC method uses this model, and so it's going to look at the residual error associated with using this model and randomly fit this model to a bunch of points. I'm going to show it in a picture in the next frame so you'll kind of get an idea. But it basically is going to take 2 points. You get these 2 observations and says, okay, well, let's look at those 2 points and if that's a track. If I only have those 2 points, well, it's maybe not a track. If I get a bunch of points in between, which are the inliers, then I might think that's a track because I've seen this same object moving along a straight line on this constant velocity model. Okay? So I'm going to look for inliers in the model, and if I've got a sufficient number, I'm going to say that's a track. Okay? And then I can repeat this for a number of iterations. So this this movie kind of shows the idea. So first it's showing, okay, here's the number of tracks. So here's a bunch of tracks. Some of these are noise. Some of these are real tracks making a motion. So you can see on the left-hand side, you can see that there's kind of a straight line. That's a constant velocity model. Some of these on the right, though, the objects are moving in a curved line, so it probably wouldn't find those as being single tracks. It would find those as being maybe segments of a track. RANSAC by itself, though, is only figuring out one of those, and it picked the one. You could see that it picked the one that it highlighted there, and now it's going through and finding it again. So it's doing the sequential RANSAC algorithm where it finds one straight line set of motions, then it goes looks at combinations of others to try to find another straight line motion. And so I believe this thing goes on and on trying to do these combinations. There's another one that it, and so here's the few that it found. So it found this one that you can see that's over on the left, the one that's a straight one over on the right at a diagonal, and then these 2 that are kind of curved, but those I think it thinks are kind of individual tracks, not groups of tracks. So the next thing we did was to look at a variation on that. So we used this, so with the regular RANSAC, it would find individual straight line tracks. And what we wanted to do was merge that or have this matched sequential RANSAC that would go and combine what we would call the Tracklet, which is the sequence of points shown in red here, with maybe another sequence of points that's going to be the curve points that shows where you're following the object. So So that's the other thing that we've done is with this matched sequential RANSAC, it'll find not only these straight lines, but it'll find the curves as well. Okay, so now the advantage of this is it's kind of a single motion model, but the disadvantage is that not many people drive it at constant velocity. The multi-RANSAC allows for the curve, allows for some combination of the tracklets. You can imagine, though, you can see how long it took just to go through those. It's kind of inefficient. It's random. You're just randomly picking these. The nice thing about the RANSAC is it does for example, it took a bunch of points, but it took a bunch of other points. And so it really looks for the cluster of points that are going to have that constant velocity model, throws out all the other outliers. So it's very computationally efficient. We've used this same algorithm for in-scene registration. If you've got one image and you want to align it with another image, you take all of these fiducial points in both images and you try to line them up. Even if you've got occlusions, the RANSAC will find groups of those fiducial points to do the matching between those tie points and leave the others behind. So the RANSAC is really a very simple algorithm, but actually very powerful. The downside is that it's computationally intensive. The next thing we did, this was kind of our own little algorithm. So, our concern about the complex motion, not just a linear motion, said, well, maybe we should just look at a proximity tracker that says we're going to form two pairs of detections that are close by, and then we're going to look for overlaps of those, and then we're going to form these tracklets to try to smooth between it. So rather than doing the random combination of pairing and then looking for the inliers, we're just going to merge these together as shown here. So even if you had two vehicles moving in opposite directions as shown on the left, it would combine 1 with 2 and 2 with 3. So when it combines 1 with 2, it says I'm moving at this velocity. Then it looks at the points around it. So it might look at point 3 and point 3 shown there. And the reason it might choose point 3 in the red, or the point number 3 in the red rather than the green, is because it's moving at a constant velocity. It's not going to take a left-hand turn as shown there in the red. And the same thing with the green ones. So it'll try to maintain that constant velocity just by using its proximity to the next one. Same thing if they're moving in parallel. Again, it would probably maintain the track in the red and in the green because it's not going to try to deviate from that straight line path. You can see, though, that there are problems there, and when I show you the results, you're going to see that this algorithm doesn't do very well if you've got parallel traffic moving together because it gets confused very easily with a slight deviation in the trajectory of motion of the objects. But we have applied this. It's low computational, does best for the isolated vehicles, doesn't do well with the parallel traffic. This is the Socorro example, where it's tracked a bunch of different vehicles all colored in different colors here and how those vehicles are moving through the environment. The next one, these are a little more difficult. So this gets to the Markov chain Monte Carlo association method. And so this first equation is you're probably familiar with Bayes' rule. And so you've got a posterior probability, which is on the left, and that's proportional to the a priori probability, which is this p sub omega. And then you've got this conditional probability. And so you're really saying that the probability of a track association given an observation is proportional to the probability of the observation given the track association times the probability of that track association in the first place. So anyways, that last term on the right is really is determined. I'm going to have to move ahead. That one on the right is kind of determined by this function, this f, which is a function of the probability of detection, probability of a death of an object, meaning that it no longer is there, the probability kind of a Poisson distribution of the birth that an object might occur, and the Poisson distribution of a false alarm. So that probability on the far right is a function of those terms. The one that's in the middle, though, this conditional probability of the observation given the track association, is again a Kalman filter. So a constant velocity Kalman filter provides that result. And then the 5 objects over here on the right are the different things that could happen. So Monte Carlo or Markov decision, Markov chains, you're usually saying, okay, how do I go from one state to another state? And there's a probability that I'm going to go from this state to the next state to the next state. Well, there's 10 states that are defined over here on the right. And those 10 states are the birth. So if I go on that top one, if I started with the set of images on, or set of detections that are on the left, then the birth, which is the red ones that are a new set of detections, how would those all be associated as one track? So that's the birth. The death is just the opposite. The next one down is a split. So what's the probability that if I have the detections on the left, what's the probability that those could be really two separate set of detections? And so there's a probability associated with that. So the Markov chain part of this is these transition matrices that allow you to do kind of your next estimate of what you think the track would be. So you combine basically the Markov chain method with a common filter within this a priori probability that things are dying or being observed or dying off. So it's this complex merge of all of these things. So the end result is that this technique works fairly well. It's flexible in that you continue doing this. So this technique is actually fairly well used. Something like this is used in particle filters. If you're familiar with particle filters, this is what the folks that are doing autonomous driving of cars are doing. Rather than a common filter which estimates the state, they take a bunch of particles and they let those particles basically propagate. So if I come to an intersection, then some of those particles are going to go off to the right on the intersection. Some of them are going to go straight, and you compute this, this map, which is the maximum a posterior probability, and you choose the one that eventually maximizes that probability. So this same sort of technique applies towards autonomous driving vehicles. So this is kind of that same Monte Carlo sort of technique, but applied towards multi-vehicle tracking. There are a lot of coefficients, like the selected birth, death, and detection rates. So the system is a pure statistician doesn't necessarily like this technique because there's a lot of fudge factor variables in it, and so you do have to play with those to make this work. So that's one of the downsides of this technique. The last technique is this Tracklet interference technique from factor graphs, and so this is very similar to a Bayesian network. So the idea is this first frame at time t0 is the first one there, and suppose that I've got this detection that it's in blue marked here, and like I said before, you want to do an association. So at the next frame time t0 plus 1, that same object might have moved to any one of these three positions. Okay? So think of this as your cybersecurity problem. You've got some sort of detection in your network at one point. You go to time t0 plus 1, and you've got maybe some detections in another place, and you want to know where somebody's traveling through your network. Same sort of idea could be applied there. You basically have to maximize your a posterior probability, and you can have a Bayesian network that goes and expands upon this. So the next frame, that same object, you can see how it fans out to probably goes to these other points. So the idea here then is let's associate a probability in your Bayesian network and then try to figure out your maximum a priori or maximum a posterior path, because eventually this can grow n factorial and explode, or you can prune the tree based on your maximum, trying to maximize that probability. Okay, so this technique also you can use to combine tracklets. So it's actually very good at finding fairly straight lines. Again, it uses a common filter. It really combines when it makes that conditional probability that goes from t0 to t0 plus 1. It's combining not only that common filter estimate, it also combines what we would call the recognition thing. Remember when I said that the more pixels you've got, the more you can recognize an object. So if say the shape of the object at t0 and the shape of the object at t0 plus 1 was the same, you would more associate that than if the shape had changed, right? So you think the shape is the same, and so you think that object is moving in that direction. So the comments are that the appearance and motion characteristics, that appearance part wasn't in the previous ones, and so if you use the appearance and if you get more pixels on target, that can help you a lot in terms of figuring out where the real track was. And the motion characteristics is again the common filter. In this technique, they kind of get merged together. They multiply the conditional probabilities together. It can handle the merging of detections. It relies on this maximum a posterior estimate problem. It uses some other techniques, and if anybody's interested, I've got a paper that describes all of the work that's done here. And this last technique has to first take a Bayesian graph, convert it to a factor tree, which then gets solved. There's some MPE solvers that you can use, and so there's software out there that you can use to solve this without writing that much yourself. So the metrics that we used, I'm really only going to talk about the first two, but the first one is really 1 minus those things that are false, like false positives, false negatives, and identity switches. So ideally in the first one, you want this to be as close to 1, so you want all those numerator terms on the second one to go to 0. And that will tell you, how well you're doing in terms of your tracking. So if you've got lots of false positives, these are tracked observations that aren't really objects, so they're just noise in the environment. Maybe it's a light that goes off, in the scene that you're looking at, and you think it's a car, and it's really not. It's just a light that's flickering. And false negatives are ones that you missed, not associated with the track. And then you've got identity switches, like if they're crossing. And then the next one is another metric is mostly tracked, and so this is the number of targets that are tracked for more than 80% of the detections, regardless of identity switches. So this chart shows, and we've highlighted here in the first two columns, those two metrics, and you can see kind of how the different ones perform over the different data sets. As I mentioned, the Socorro is a simulated data set, so you can see the one that provides the best capabilities, this proximity tracker. It worked fairly well because there weren't a lot of cars that were driving side by side. The next one, the Crest, remember there were only 11 objects that were truth. It says down here in the lower right, only 11 vehicles were actually truth. And so there were a lot of other, though, false alarms that caused the this MOTA metric to go down. So you can see it didn't do as well, but the other one that was mostly tracked did well. And then you can see for the Air Force Research Labs that the proximity tracker did well. The factor graph actually did very well, though, in the bottom two cases. So you can see the factor graph does pretty well. The only one it didn't do very well on was the Crest, where there were some issues associated with too much noise and not enough targets to be tracked. And this is an example of what the movie looks like from the Crest. So there we're following a single target. Now we're following 3 targets. Now one of those targets is splitting off. And so this is the sort of data that we're trying to, you can see that it lost this one target at the intersection, but it's following the other 3 as they made their turns. Okay? So again, think of that as a computer network, and you've got intruders that are going through your intruder network, and you might apply these techniques towards cybersecurity as well. So in general, no was a clear superior winner according to the metrics. I hope that what you got out of this presentation was really the use of RANSAC. Again, if you haven't heard of RANSAC before, you probably will sometime in your career. It's used very often for in-scene registration and other techniques. The Monte Carlo, the Markov chain Monte Carlo techniques, you've surely heard those, or you will hear those. Those same sort of techniques could apply towards many of your problems. There's, of course, the more information you have, the better you could always do, right? So if color, so the camera that we had down looking from the Crest was not using color. And so the more you have in terms of, if I had a person who was moving across and they were wearing a bright red hat and they were moving through an airport environment, I could probably see them fairly well. If they're wearing the same clothes as everybody else, same colors, it's going to be hard to track them. Same thing with cars and anything you're tracking. The more distinguishable the feature, the more you can pull out that object. And then, the better your models, the straight line, constant velocity models are a limiting factor. If you have more complex models, the disadvantage is the computation goes up. The advantage is it might do a better job of tracking maneuvers. Okay? Anybody have any questions? Yes?
For what it will be used, like tracking the cars, maybe for traffic reports, or what is the objective, the goal of tracking?
There are actually already systems that do some tracking of traffic. For example, the red light monitors. When you're getting onto busy intersections. We did this mainly for looking at potentially out in the future. Sensors are getting more and more resolution. You see UAVs and things like that that are flying around now, and people are interested in tracking more objects, whether it's areas where we're worried about terrorists or things like that. But we don't have a specific application. We're pushing the technology right now, but for a lot of our remote sensing, we're interested in not necessarily cars, but other things that we might be tracking, and we want to make sure that we've got the best available algorithms. And so the beautiful thing that's happened over the last 20 years is computing gets doubling every 18 months. And so some of the algorithms that we're using today, we never would have used 10 years ago. And that's what this is really looking at, is as computing gets bigger, you've got more and more capabilities. And we've got some systems that have 52 racks of computing equipment doing image signal processing sort of algorithms. GPUs have just, quadrupled the number of cores of processing that you've got. So you're able to do things you never could do before. Yes?
Is it possible to synchronize this with the GPS location of the cars in one location and then think about how they are mapping their path or something?
Yeah, I don't know what particular application you're thinking of there. We have looked at some things, what we call a constrained velocity match filter. So if you kind of know where the road is, straight, and I think GPS they have techniques for doing this right now. You can formulate it as an optimization problem where you're trying to minimize the error of tracking along the, if you think the cars aren't going off-road and they're going to stay on the road, you can minimize the error of the vehicle on the road and, use that to increase your signal to noise. Okay, so it ends up that if that object is moving, one way to increase your signal to noise is co-add or add up the frames, but you've got to know kind of the velocity they're moving at. And so you add up those velocities by adding them together. So it's a kind of a chicken and egg. Which do you know first? If you knew the velocity that they were moving, then you could add them up so that your signal to noise sticks out further on these. So you kind of, there's different techniques for doing that. You can actually kind of do a random search around where you think there might be something moving at a constant velocity and go and add those up. So anyways, yeah, I think there are papers out there where people have looked at, combining GPS with the visual tracking. And in fact, some of the robotics areas, they use visual techniques combined with GPS. So in robotics, they particularly have a problem with, you get GPS and then you go into an urban canyon and the robotic vehicle doesn't get GPS and it starts to drop out and you need to kind of dead reckon, and they use computer vision to kind of guess where you are, and they combine that with the GPS, much like you combine inertial measurements with GPS for guidance of things like missiles. Okay. Anybody have any ideas for network applications? Cybersecurity? No? Okay. Great. Thank you all for coming. And please pick up one of the either the things here, the booklets, or the what is that guy? Einstein. Pick up Einstein. There we go. Great. Thank you.